Hey guys, so in this video we're going to go over some practice problems that'll be very similar to what you see on the exam. So first we'll cover relative humidity. Relative humidity is a ratio of the actual vapor pressure in the air over the maximum possible vapor pressure of that air. In other words, this is how close the air is to reaching full saturation. So this will give us a ratio fraction. We take that fraction and simply multiply it by 100 to get the final relative humidity percentage. And I'll show you a few example problems of that now. So in example 1, we have an actual vapor pressure of 16 millibars here and a maximum vapor pressure of 20 millibars. So what we do is we take the 16 millibars divided by 20. That gives us a reduced fraction of 4/5. We take that 4/5 ratio fraction, multiply it by 100 to get 400/5, which gives us our final relative humidity percentage of 80%. Now in example 2, we have an actual vapor pressure of 6 millibars here and a maximum possible vapor pressure of 30 millibars here. So again, we take the 6 millibars, divide it by 30. That gives us a reduced fraction of 1/5, which we multiply by 100 to get another ratio of 100/2. 6 millibars divided by 30 gives us a reduced fraction ratio of 1/5, which we multiply by 100 to get another ratio of 100/5, which gives us the final answer of 20% relative humidity. So next we'll discuss some problems about adiabatic temperature change that you might see on your exam. The examples I'm going to give you are very similar to what the problems on your exam look like. We're not going to give you very tricky mathematical calculations, but you will need to know when to use which type of calculations in the proper order. So I'm going to cover that now. So in example 1, we're dealing with an unsaturated air parcel. The sea level temperature of the air parcel is 30 degrees Celsius, and we know that the dew point temperature is 10 degrees Celsius. And the question we're answering here is, at what altitude does the air parcel become saturated? So we already know that the dew point temperature is 10 degrees Celsius. And remember, the dew point temperature is the temperature at which air becomes fully saturated. So essentially this question is asking, at which altitude does the air parcel reach the dew point temperature? So that's what we're going to figure out here. And because we're dealing with unsaturated air here rather than saturated air, we have to use the dry adiabatic rate, which means that the air will cool by 10 degrees Celsius per each 1,000 meters that it rises. Because remember that as air rises, it expands and it cools down. So to do this calculation, we start at sea level, 0 meters, with our known temperature of 30 degrees Celsius here. So first we increase the altitude to 1,000 meters, which means we have to subtract the temperature by 10 degrees Celsius, according to our dry adiabatic rate here. So we go from 30 degrees to 20 degrees Celsius at 1,000 meters. And then we repeat the process again. So we go from 1,000 meters in altitude to 2,000 meters in altitude, and we decrease the temperature by 10 degrees Celsius again, from 20 degrees Celsius to 10 degrees Celsius. And we already know that 10 degrees Celsius is the dew point temperature. So that is the temperature at which the air becomes fully saturated. So that gives us our answer. Our answer is 2,000 meters. That's the altitude at which we reach the dew point temperature. So now example 2 is a follow-up question to example 1. What is the temperature of the same air parcel at 5,000 meters high? So we simply take the information that we learned in example 1. At 2,000 meters high, the temperature of the air parcel is 10 degrees Celsius, which is the dew point at which the air becomes fully saturated. So as we increase our altitude, the air was already saturated at 2,000 meters, and it only continues to be saturated as we go higher up. So because we're dealing with a saturated air parcel, as this parcel continues to rise in altitude, we have to use the moist adiabatic rate instead. That means that the air cools by 6 degrees Celsius per each 1,000 meters that it rises, rather than the 10 degrees Celsius when the air parcel is unsaturated. When it's a saturated air parcel like this, it cools by 6 degrees Celsius per 1,000 meters. So again, our question here, we're trying to find what is the temperature of the air parcel when it reaches 5,000 meters in altitude. So we start at our base point of 2,000 meters. The air parcel is at 10 degrees Celsius. So to go up to 3,000 meters, we know that based on our moist adiabatic rate, that air is going to cool down by 6 degrees. So we subtract 6 degrees from 10 to get 4 degrees at 3,000 meters. And we repeat that process 2 more times. So to go from 3,000 meters to 4,000 meters, we have to subtract 6 degrees again. So it goes from 4 degrees Celsius here to negative 2 degrees Celsius here. Then the final step is to go from 4,000 meters up to 5,000 meters. And again, we subtract 6 degrees more. So it goes from negative 2 degrees Celsius to our final answer of negative 8 degrees Celsius. At 5,000 meters high, the temperature of that air parcel is negative 8 degrees Celsius. So we're using the moist adiabatic rate to solve that problem because the air is saturated in this problem. Whereas in example 1, it was an unsaturated air parcel. So now our final example problem, example 3, really puts everything together, but just in reverse, and it really tests your